Hello, everyone, and welcome back. In the previous video, we introduced functions of a single variable, that is, functions that take a real number and produce another real number. Now, it's functions that are going to be the focal point of the remainder of these video lectures. And last video, we introduced the basic concepts of limits of a function. Now, you may have encountered limits in a previous, maybe introductory calculus class, and we know that we have this sort of shorthand way of writing them, lim x to a of f of x. And we can determine whether or not it exists or not with fairly basic routines. But what we saw in the previous video is that we can actually make it very, very precise to talk about the limit of a function. And this is, sort of going one level down into the analytical realm where we introduced epsilon delta notation. Now, the other thing that you probably know about limits is that they are closely associated to continuity of a function. And importantly, there are three varying levels that we can think of for understanding continuity of a function. The first one, at the very highest conceptual level, is that you can draw the function without ever lifting your pen. And this is a really good visual way of understanding what it means for a function to be continuous. But the unfortunate part is it doesn't really lift into functions where you have a higher dimensional domain or a higher dimensional output, because we can't draw these things very well. Then the sort of layer down is probably what you encountered in an introductory calculus class, where you say the limit as x approaches a not only exists, but it's equal to the function at that value. So the limit exists, that's what we talked about in the previous lecture, but also you say that the limit is actually what it should be based on the value of the function. Now, what we're going to do today is we're going to go another level down into the very, very analytical realm, just like we did with limits, and introduce an epsilon delta notation for how we can precisely say that limits or that a function is continuous at a certain point. And what we'll see through some of our examples today is that this can abstract us into very, very, very complex functions that we just can't even draw. And we can determine where these things are continuous and where they are not. Now, as with all lectures in this series, we're going to start with a definition, and we're going to use that definition, in this case of continuity of a function, as our motivation to work through a number of results and see how we can conceptually understand continuity at an analytical level. So let's go ahead and present the definition, the true definition of continuity of a function. So let's say a function f is called continuous. So let's put this in red. This is the active term here, so continuous. At a point A in D, the domain of F, provided, so here's our epsilon delta notation, provided that for all epsilon greater than 0, there exists a delta greater than 0, very similar to what we saw with limits, epsilon delta notation, and such that if x belongs to the domain and it's within delta of your point, so this is just like what we did with limits, with limits, then this tells us that f of x minus f of a is less than epsilon. Okay, so let's just pause there for a moment and think about how this differs from a limit. Two things that come into play here. First of all, a doesn't have to be a cluster point. That was something that we needed for limits. Second thing, you are actually allowed to have x equal to a. And that is that stipulation that you probably learned in calculus, where you say the limit exists and the limit is equal to the function. That's what this is saying right here. Because with a limit, that would have been L. But here you're saying L has to be the value of the function at the point you're interested in. And we can abstract this a little bit. We say if f is continuous at every point x in D, we say F belongs to the set C of D. C stands for continuous functions on the domain D. So that is the set of all continuous functions. Functions on D. So this is just an abstract way of picking a continuous function on a domain. This is similar to what I would say maybe if, say, let X be an R. X is an element of the real numbers. The real numbers are a set of numbers that we can choose elements from. Well, you have the same abstract way of thinking about this with the set of continuous functions on a given domain D. So I can say, you know, instead of me writing let F be a continuous function on the domain D, I can say let F be an element of C of D. Now there's a couple little remarks here. The first of which is that if D is equal to some interval, so such as maybe a closed interval, A to B in R, we write, so we denote C of D by C of AB. So we just sort of drop the extra set of brackets so that things aren't confusing here. So that's our first case. And the second case is there's a degenerate case for continuity here. So if there exists a delta greater than 0, such that the domain intersected with this neighborhood of delta, if that thing is just equal to A, right? So there's sort of no wiggle room around A, right? It's not an interior point. It's not sort of, it's, you know, there's not an open set that goes around this thing. Then continuity, then the stipulation for continuity is automatically true. True for X equal to A. And that's because, so because f of X minus f of A, this can only be f of A minus f of A, because the only X's you can choose from is A, because there's nothing around A to look at, which is equal to 0, which is less than or equal to epsilon, and that's for all epsilon greater than 0. So that's like a sort of degenerate case, right? Imagine you just have a function that's defined at a single point, say X equal to 0, automatically continuous by the definition, because there's nowhere else to look around 0. So it's a sort of weird degenerate case for this definition of continuity. And we'll look at an example of this later. But this leads me to another sort of natural definition, the sort of opposite of a cluster point. So we call a point A in the domain an isolated point. So the opposite of a cluster point of your domain D and R, provided that there exists a delta greater than 0, such that if you look in the domain in a neighborhood of your point, the only thing you can look at is A. So there's no wiggle room around A, right? So this is exactly the case that I articulated. You know, this tells you that functions are automatically continuous at isolated points. That's essentially what that's saying. So, you know, isolated points aren't really that interesting, right? When we talk about limits, we talk about cluster points. We want to know what happens as you get close to these things, you know, without actually being at them. So isolated points are like a degenerate case that are not really that interesting. Okay, let's provide our first theorem. We remember one of the nice things, or continuity, sorry, if we look back at this definition, The definition of continuity and the definition of limits looks a lot alike, and we already know that they are a lot alike. So let me start with a theorem that tells you, exactly how these things meld together. So we say a function f is continuous at a cluster point. So again, if we're going to talk about limits, we need cluster points. So a cluster point A in the domain of f, df, if and only if the limit as x approaches a of f of x, well, this thing has to actually exist, and that limit is equal to the value of f at a, the point you're interested in. So this is what I started by talking about. We sort of looked at this with the definition. I'm just going to make this precise with this theorem. And again, this is probably, if you did an introductory calculus course before this, you probably used this definition, right? You took some limits and you checked that it was equal to f of a. Usually the common exercises are with piecewise functions. You just need to check the limits from the left and right are the same, and then you need to say that they equal the actual value of the function. So this theorem is everything that you've been using so far. So then the proof of this, well, this is a proof, this is an if and only if statement, a logical equivalence. So that means that we need to prove both directions. Let me prove the left to right direction first. So that means first, suppose f is continuous at a in the domain of f. Okay, so this means that is for all epsilon greater than 0, there exists, so I'm just using the definition of continuity here, there exists a delta greater than 0 such that if x minus a is less than delta and x is in the domain, that's what that intersection said. But I'm just going to pose it like this so you can see it in terms of maybe the definition of continuity or of limits, so that everything is sort of becoming crystal clear. This implies f of x minus f of a is less than epsilon. So that tells you sort of hence, for all x in the domain of f, such that, well, 0 is less than x minus a, which is less than delta. So basically just looking at, everything that satisfies the definition of continuity except the actual point x equal to a, we have f of x minus f of a is less than epsilon, right? Which by definition, so which implies the limit as x goes to a of f of x exists and equals f of a. Okay, so that actually, it's more writing than it was actual thinking. And that just comes from the fact that the definition of continuity sort of subsumes the definition of a limit. The only difference here is that continuity allows you to take x equal to a. So this implication here, you just said, okay, it works for every value from a minus delta to a plus delta. Well, then limits just want me to do the same thing as long as I don't look at a. Okay, of course, it still works, right? Because all I did was plucked an element out of the domain. So then what happens if you go the other way? So now we can suppose that the limit as x goes to a of f of x exists and equals a. And we want to show, or sorry, equals f of a. We want to show that f is continuous at a. Well then, for again, using the definition of continuity, then for all epsilon greater than 0, there exists a delta greater than 0 such that if I look close to x, or sorry, if I look close to a, but not actually at a, this implies that f of x minus f of a is less than epsilon. And in this case, I'm substituting L is equal to f of a, right? Because I know what the value of the limit is equal to. So I'm just using the definition of a limit here. Nothing fancy, right? I literally just wrote down the definition with L is equal to f of a, just transcribing what I know. But clearly, if I include x equal to a here, well, trivially, f of x minus f of a is equal to 0 when x is equal to a. So I can easily just add one more point into the domain and make this work. So this implies that for all x in the domain near a, so essentially all I'm doing is adding a back into this because that's the only extra requirement that continuity needs. We have f of x minus f of a is less than epsilon, so that f is continuous. CONT dot, that's my short form for continuous at a. So, this is a really, really easy proof, right? And the proof is just requiring you to really understand the definitions of the limit and the definitions of continuity. And in this case, the only difference is one includes x equal to a and the other one doesn't. And you can see that just by putting that in, by the fact that you know that your limit is equal to f of a, then everything is okay here. But the nice thing is we have a really sort of simple corollary that comes out of this that is probably going to be the most useful thing for you, because remember we said we can put limits in terms of sequences. That means we can put continuity in terms of sequences as well. And again, we probably like sequences more than epsilon delta notation. I find it much easier to work with because you spend a lot of time understanding sequences. Think about the first few video lectures. They're all about sequences. You're probably pretty good with them by now. So here's the real benefit. This corollary says a function f that transports you from its domain into the real numbers. This is just the notation that says it has domain D, is continuous at a point A and D if and only if it satisfies the following. Now I'm going to write this in green so it stands out a little bit to you, because this is another criterion. This is the sequential criterion for continuity. Remember, we had the sequential criterion for limits in the previous lecture. So we have the sequential criterion for continuity. And this says for every sequence xn approaching a with, of course, xn has to be in the domain because you have to be able to evaluate the function of these points. We have f of xn is approaching f of a. So again, maybe you want to pause the video and go back and look at your notes and look at the sequential definition, sequential criterion for limits. Only difference was f of a was replaced with L, the limit. Again, the difference here for continuity says we're allowing ourselves to actually be at A. Okay, let me do the quick little proof here. It's again, the proof is fairly quick and dirty and easy. Actually, it's not even dirty. It's quite clean, actually. I don't know why I said that. But we sort of have two cases. So case one, we have to look at an isolated point, right? So in this case, if we look at the definition, we didn't say it's a cluster point, so it could be an isolated point. So let's do the easy case first. Suppose A is an isolated point. Of D. In this case, there's very little to do, right? Because then F is automatically continuous at A from what we've already said, right? So F, so this implies F is automatically continuous at A, no matter what. Doesn't even have to satisfy the sequential criterion, right? We just have to show the sequential criterion is also true in this case, right? So we don't even have to do logical equivalencies. This is much easier. Now, since xn approaching A, in this case, implies, now again, this thing is an isolated point. It means you can never get that close to it. You're always some distance away from it. So if you have a sequence that's converging to A, and this thing is an isolated point, this implies that there exists some natural number that if you look at the sequence beyond that natural number, this implies that you have to actually be at A, because you can't get close to it. The only way you can get close to it is actually being at it. But then this also tells you that f of xn is equal to f of A, which implies f of xn is a constant sequence of, or it's an eventually constant sequence, and so therefore converges to A. So that's super, super simple, right? And the point of this is isolated points, you can't get close to them. So, there's sort of a degenerate case of continuity because you automatically satisfy the definition. Okay, so obviously the much more interesting case is going to be if we have a cluster point. So let's say, suppose A is a cluster point. PT stands for point of the domain D. Then we can just apply our previous work, right? So some of the theorems that we've done in the past. So we say if f is continuous at A, this implies that the limit as x goes to A of f of x exists and equals f of A. Hence, the sequential criterion for limits, not for continuity, for limits, so from the previous video lecture, this implies that the sequential definition, that the sequential or criterion for continuity is satisfied. So all you had to do was use the previous theorem to say, okay, f is continuous at A. That implies the limit is x goes to A of f of x is equal to f of A. But then we already showed that that limit is equivalent to taking sequences. And so therefore, that gives you the sequential definition of continuity, or the sequential criterion for continuity. And then so conversely, if the sequential criterion, so it's a lot of writing here. Again, this is a corollary. Corollaries are typical or typically like automatic from what we just proved. And that's sort of what we're seeing. That's why it's taking me almost more time to explain or to write it than it is to actually do any math. So if this is satisfied, then the limit as x goes to A of f of x exists and equals f of A, f of A. But from the previous theorem, this tells you f is continuous at A. All right, so there's really nothing to prove, right? Essentially, it's just making sure that you understand the definitions of continuity, the definitions of limits. And it's really just playing this little sort of shell game of saying, okay, I have continuity, all right, then I just sort of switch it out for limits. And I have limits and I sort of switch it out for continuity. That's all that's going on here, right? I'm not doing any magic, nothing fancy. It's just arguing from definitions. So that's all that we've done today. It's nothing, it's not like interval halving or these really, really complicated proofs that we've done so far. It's really just arguing from definitions. Okay, So remember in the previous lecture, we had this idea of adding and subtracting limits or multiplying limits or dividing limits. Well, since we've put continuity in terms of limits, we get all of the same things for talking about continuity of functions. So let's go ahead, let's present a nice theorem that summarizes all of this. So suppose f and g are continuous. Sorry, it's continuous at some point that is in both of their domains. So df stands for the domain of f, dg is the domain of g. Then let's say, well, then f plus or minus g is continuous at a. Same thing, f times g is continuous at a. 3, you know what's coming. F divided by g is continuous at a. And this is, of course, provided you're not dividing by 0. So provided g of a does not equal to 0. And again, you've seen that, right? That's how you determine where, say, rational functions, polynomial divided by polynomial, that's how you would determine where they're continuous, right? You just look for where the domain is not 0. I mean, where the denominator is not 0. And the last one here is composition. So something a little more exciting. So if, moreover, h is continuous at f of a, then the composition and this is denoted h of f. Remember, this is you evaluate h at the value of f of x. This thing is continuous at a, where, and again, just so you know, this notation means h of f of x. Okay. The nice thing is this is a very, very, very powerful theorem, right? This sort of underlies everything that we do in sort of an introductory calculus class. And the nice thing for us is it's powerful and it's going to be very easy to prove because we've got the sequential definition now. And we know the sequential definition sort of makes things much easier because we already have a proof of something similar for sequences that we proved in one of the first lectures. So let me just show you what I mean. The proof of 1, well, let's say that if xn is converging to a, with xn being common in the domains of f and g, so I need it to be in both domains so that I can evaluate f and g at these points, then we know f of xn approaches f of a. That comes from the sequential definition of continuity, or the sequential criterion, pardon me. And similarly, g of xn is approaching g of a. So the nice thing about the previous results is that we can always sort of swap out epsilon delta continuity for sequential continuity. And as you can see, makes life way easier. Then we conclude, you know, it's not even really worth sort of writing this out. Again, it's going to be one of those things, more words than it is actual than work. So we get the limit as x goes to a of pardon me. We get f of xn plus or minus g of xn. Well, since you can add or subtract limits here, these things are sequences. This is f of a plus or minus g of a, which therefore implies that the limit as x goes to a of f of x plus or minus g of x is equal to f of a plus or minus g of a. And that is all you need to show that that thing is continuous. Maybe I won't put the tombstone there because we're still going. But part 2, this is nearly identical to to part one, right? And again, if you need to review this, go back and see what we did with limits, and then go back and see what we did with sequences. Same thing. Again, part three, nearly identical to sequence case. So what I mean by the sequence case is when we said that if you take xn converging to m, or xn converging to L, yn converging to m, then if m is not 0 and none of the y's are 0, then you can divide these two things. Again, we proved this in lecture, so maybe go back and take a look at that. But this is not really that interesting because we translate everything into sequences and we sort of just evoke those previous theorems. Okay, let's do the one that's sort of interesting here. So first of all, we're going to do the composition. So we're going to note that, well, the domain of H of F, this is the set of X in the domain of F such that F of X is in the domain of H, right? So this is a two-step carryover. Pick an X, transport it forward by F, and then transport F of X forward by H. So now let's let Xn be a sequence in the domain of H of F such that Xn is converging to the point A. Remember, we want to prove that H of F of X is continuous at A. Then so we're going to define a new sequence, call it Yn. This is F of Xn. We have, well, again, it's fairly simple. You're just sort of using continuity because this gives you the limit as n goes to infinity of H of F of Xn. Well, this is equal to the limit as n goes to infinity of H of Yn, just sort of by definition. But Yn is a sequence converging to F of A, which we know H is continuous at. So this becomes H of F of A. And so maybe we'll just put a little note under here. This is because Yn is converging to F of A and H is continuous at F of A, right? And so therefore H of F is continuous at A. So this is the real beauty of all of these sort of equivalent ways of talking about limits and continuity, because we can sort of swap in and out, whatever suits our purposes at that time. And so, what you can see is that I'm using sequences here because I think that they're much easier to work with. I've sort of articulated this before, but you can do this in terms of limits if you wanted, or you can do this in terms of epsilon deltas if you want it, right? It's all going to give you the same results. You just have to pick, which one of these equivalent statements you think is the easiest for you to work with. And again, personally, sequences. I love sequences. I think they're super easy to work with compared to, the really strenuous epsilon delta stuff that we've seen. Okay, so we've had a little bit of fun. We've got some theorems down. Let's do some examples. And let's start, almost trivial. So example 1. Let's let I of X equal to X. So this is the identity function, right? You pick a number, I just say that number back to you. You say 2, I say I of 2 is 2. You say pi, I say I of pi is pi. You say minus 64, I say I of minus 64 is minus 64, right? So that's why we say I, it's the identity. And then this is for all X and R. Well, it's not really hard to see, then I is continuous at every point A and R. Why? Well, if you take Xn converging to A, then I of Xn is equal to Xn, which converges to A as well, which equals to I of A. And so, done, right? Nothing interesting. You're just feeding in a conversion sequence and you get out the same conversion sequence. Not really that interesting, but it's important to note, right? We want to know this. And this just reinforces things that we took for granted in maybe introductory calculus. Okay, let's look at another super simple trivial one. F of x is equal to c, a constant. All right, now again, not an interesting function, but this is super easy. If xn is converging to a for any a and r, then f of xn is equal to c, which clearly converges to c. It's just a constant sequence. Like, it's almost like hurts my hand more to write this down than it is to hurt my brain, as n goes to infinity. And c is equal to f of a, which implies f is continuous at every a and r. And so, using that cool new notation here, this tells us f is a continuous function on the entire real line. It belongs to C of R, right? We have a new set to talk about, so we can show off some fancy language now. Similarly, in the last case, the identity function also gives you f belonging to C of R. And so let's put it all together. Well, then we can say let f of x equal to x squared for all x and r. So you give me a number, I square it. Well, note f of x is equal to I of x from example 1 times I of x. So from the previous theorem, so we have f is the product of two continuous functions. This implies that f is also continuous for every value of r. And of course, moreover, every polynomial, so any polynomial, p of x, let's say, a n x to the n plus a n minus 1 x to the n minus 1 all the way down to a0 is such that p belongs to C of R. It's continuous everywhere. And again, you're just sort of applying this inductively, right? So you say, well, first an times x to the n, that's going to be continuous because x to the n is just continuous function x times x times x times x n times. And an is a constant function. So from part 2, we show that, or from example 2, we showed that's continuous. So then an x to the n is continuous. Same argument applies to an minus 1 times xn minus 1. So you add those two together, continuous. Then, you just keep adding. It's just this inductive process that tells you that, every polynomial is continuous at every value of x and r. Also, every rational function. Again, these are things that you probably took for granted in introductory calculus, where we call it Q. Again, Q stands for rational because Q means quotient, and rationals are quotients, right? And so we get P of x divided by Q of x, where P and Q are polynomials. Well, this is a continuous function divided by a continuous function, and so this is continuous for all x such that Q of x does not equal to 0. Of course, you already knew this, right? You did this, in an introductory calculus class, and this is a typical exercise, where is the function continuous, and you have to sort of weed out the zeros of the denominator. Okay, so I'm sort of, going over things that we might already know, but it's important to reinforce this, and now we've proved it, so you can believe it, right? Okay, let's do another one. Let's do a piecewise function. Let f of x equal to 1 if x is greater than or equal to 0, and 0 if x is less than 0. Now, this might look familiar because we worked on this one in the previous example of limits. So since the limit as x goes to 0 of f of x does not exist, remember we proved that in the previous lecture, This implies f is not continuous at x equal to 0. Right? This comes from the equivalence between continuity and the limits. So if the limit doesn't exist, therefore you cannot be continuous there. There's no f of a to evaluate. Well, there is an f of a, sorry, that's equal to 1, but there's no limit that approaches f of a. But I will leave it to you to check f of x is continuous for all x not equal to 0. And that's pretty easy. That's just because you're a constant function at every other point than x equal to 0. Okay, let's look at another one. This one's kind of fun. Let f of x equal to, okay, it's going to be 1 if x is greater than or equal to 0. So on all the positive numbers, this returns the constant function 1, and 0 if x is equal to -1. Now the question is, is f continuous? Where is it continuous? Well, again, f is continuous for all positive numbers, so all x greater than or equal to 0, because it's just a constant function. So you can just repeat this argument from point 2. Instead of saying that f is defined for all x and r, you can say it's defined for all x greater than or equal to 0. So clearly, f is continuous for all x greater than or equal to 0. Now the question is, what about this point x equal to -1? Well, that's an isolated point. So maybe let's put a little comment here. X equal to -1 is an isolated point. You thought that I forgot about that, right? Well, we're automatically continuous at isolated points, right? It's separated from the rest of the domain. You have -1 way over here, and then all the positive numbers way over here. So we're continuous everywhere. So f is continuous at every point in its domain. And as you can see, these isolated points, even if you're continuous at them, they're still not really that interesting, right? Because there's nothing really happening close to them. You just pick a random point and you say, okay, then, just if you put -1 into here by chance, then you can have 0. Other than that, I'm only going to accept non-negative numbers. All right, let's do one last one. And this one is genuinely interesting. Remember, I said at the very beginning of this lecture that, this idea of being able to draw a function without lifting your pencil is good, but it has some flaws. And my example was that's when you have higher dimensional either domains or ranges. But let me show you an example where this is gonna fail miserably. And so we're left to understanding this with like true analysis. So this thing is going to give you x squared if you put in a rational number, right? So 1/2, that's fine. I'll give you 1/4 in return. But if you put in an irrational number, then it's going to give you minus the square of that thing. So maybe you put in pi, right? Well, it's going to give you -pi². Or you put in √2, it's going to give you -2. So the question is, where is this thing continuous? And you can't draw this. There's no way you could draw this because the rational numbers are dense. They sort of fill up the entire domain. But then there's all these little cracks that are the irrational numbers. So there's no way we can draw this. We're stuck with pencil and paper here. Well, we claim that f is continuous at x equal to p. So P stands for point if and only if P is equal to 0. So essentially what I'm saying is the only place that this thing is continuous is at P equal to 0. Okay. So how do you see this? Well, first what we're going to do is we're going to rule out that it's continuous anywhere else. So here, step 1, f can only be continuous, at x equal to 0. So this is my first step, right? I'm not going to prove that it's continuous at x equals 0. I'm going to prove that it can't be continuous anywhere else. Well, then let's say let xn be an element of the rationals. So I have a sequence of rational numbers such that xn is converging to p, and let yn be a sequence of irrational numbers such that yn is also converging to p. Okay, so I have two sequences converging to p. The sequential criterion for continuity says that when I plug these things into my function, they are themselves going to converge to f of p when you have if this thing is actually continuous at p. So if f is continuous at p, then now I don't need to separate this out. I don't need to know if p is rational or irrational. Let's just look at the sequences that are coming out of this thing. Okay, so then f of xn, this is going to be xn squared, right? Because xn is a rational number, which we can use the fact that xn squared is the convergent sequence xn multiplied by the convergent sequence xn. So this converges to p as n goes to infinity. Similarly, f of yn, this is an irrational number, so you get minus yn squared. But again, these are continuous, these are convergent sequences, yn times minus 1. And so therefore, this converges to minus p squared. Sorry, I forgot the squared up here. As n goes to infinity. And so if f is continuous at p, then these two limits have to equal to each other. So p squared is equal to minus p squared, which implies that p is equal to 0. So what this shows you is that the only way that you can be continuous is if p is equal to 0. You are not continuous anywhere else. And this speaks to the sort of density of the rational numbers, right? They're sort of interspersed in everywhere along the real numbers. And the only way that you could potentially hope for continuity is when x squared and minus x squared are super small because they're close to 0. That's the only time that those things actually sort of match up, is at 0. Okay, so then step 2, we prove f actually is continuous at x equal to 0. Okay, so how are we going to do this? Well, let's suppose xn is any sequence, doesn't have to be of all rationals, doesn't have to be of irrationals, anything you want, converging to 0. So we're going to use the sequential criterion for continuity here. So that means that we need to prove f of xn converges to f of 0, which is itself equal to 0. Okay, so again, we're using the sequential criterion for continuity here. Well, since we're dealing with convergence, we need an epsilon greater than 0. And we can note that xn squared goes to 0 and minus xn squared goes to 0 as n goes to infinity, right? So this is just sort of obvious to us. Moreover, there exists a capital N and N such that if I choose n greater than or equal to n, this implies, well, since xn squared is converging to 0, this thing is less than epsilon, right? So I'm using the fact that xn squared goes to 0. But it turns out that this capital N is also going to work for my minus xn squared sequence. So it follows that if n is greater than or equal to capital N, this also implies, well, minus xn squared minus 0, which is again equal to xn squared. This thing is equal to epsilon, or sorry, it's less than epsilon. So don't get confused here. The first xn squared minus 0, that is the sequence xn squared converging to 0. The minus xn squared minus 0, that's the sequence negative xn squared converging to 0. But that essentially covers both cases, right? If xn was rational or if xn was irrational. So this says now let let n be greater than or equal to capital N. So we need to look far enough in the sequence. And so if xn is a rational number, then f of xn minus 0 is equal to xn squared, which we already proved is less than epsilon, or we already said is less than epsilon. And on the other hand, if xn is not a rational number, then we get basically the same thing, because f of xn minus 0, this is equal to minus xn squared minus 0, which we already showed is equal to xn squared, which is less than epsilon. So we covered both cases, right? If you look far enough in the sequence, you say if it's rational, still going to give you a less than epsilon. If it's irrational, going to give you less than epsilon. And so thus, taking n bigger than or equal to capital N implies f of xn minus 0 is less than epsilon, so that f of xn converges to f of 0, which is 0 as n goes to infinity. Therefore, f is continuous at x equal to 0. That's how you do it, right? So it's much easier to rule out where you're not continuous, right? That was pretty easy because we just had to come up with two sequences that don't give you the same limit. But proving that it is continuous, it takes a little bit more work, but nonetheless, it's fairly routine, I think. Okay, so what we did in this lecture is we extended our discussion from the previous one. That's how you should really think about it, right? We took the concept of limits and we added in, or we extended it to the concept of continuity. And that's really what a lot of our theorems said today. They said that you can always think of this epsilon delta definition of continuity in terms of our limit definition. And from that limit definition, that extended us up to the sequential criterion for continuity. That was just a natural extension of the sequential criterion for limits. And so, in my opinion, this makes dealing with continuity much easier because this puts everything in terms of sequences, which again, I cannot emphasize enough, is typically easier to work with than these epsilon delta definitions.